Okay, so far we have discussed some mechanism on how to model our noise and how to investigate what type of noise that affected our image. Okay, image, the noise itself is a random signal. So one way to, okay, the only way to model our noise is through provide the PDF. Okay, in other words, PDF is actually represent the noise models. Okay, and then that in doesn't matter is it practical or hand calculation. Okay, the step is similar, meaning that you need to capture the image, the homogeneity image, which you can obtain from your, in which you can be obtain that kind of image by taken a plain wall, a plain surface, because that can provide the very homogeneity pixels, and can provide a very, very similar intensity value or homogeneity intensity value of that kind of plane surface. So from that, if after you capture a plane surface, then you need to, that is the first step. Once you get that one, then you can plot the histogram of that image. Okay, this one I just show you the how to do the hand calculation. Okay, doesn't matter is it using hand calculation or using if you try to solve a practical example like this one, the step is similar, meaning that first you need to plot the histogram. Okay, seems close to this one. We need to plot the histogram, and then from the histogram, because why we need to plot the histogram, because that is how that is the only way for us to produce the PDF. Okay, because if you want to produce the PDF or that image, then you need to go through the histogram. And once you produce the histogram, once you produce the PDF, then you need to investigate the shape of the PDF. If the in this case, if the shape of the shape of the PDF is in bell shape, then you can say that the noise that affected this image is a Gaussian noise. And if you talk about the Gaussian noise, this is the how we express the that noise model, which is by using the PDF, by using the Gaussian function. And of course, if you see this Gaussian function, there's a two parameter that you need to fill in with some number, which is the mean and the variance. So in order for you to measure the mean or to calculate the mean and variance, then you need to calculate the by using this formula. Okay, and then that is for this example is it's related to Gaussian distribution, or it's related to Gaussian noise. Okay, so that's why when we if you talk about the Gaussian noise, this is the only two parameter that you need to measure, which is the mean and the variance. And in order for you to measure the mean and the variance, then you can simply use the formula, the given formula, which is this one or this one. Okay, which is the one that has been provided in the slide here. Okay, however, like I mentioned previously, when we talk about noise, it is just not only can be modeled as a Gaussian model or Gaussian noise. Okay, there's a several model that you can there's a several function that you can use to represent your noise. Okay, in other words, in other words, what I would like to explain here is that instead of Gaussian function or Gaussian distribution function, okay, that can represent the random signal also can be represented by other model as well. It's not just a Gaussian noise, the Gaussian distribution function. Okay, that is because why we always familiar with Gaussian, because Gaussian is the only one that is always seen by us. Okay, that's why another name for Gaussian distribution function is normal distribution. That does not mean we don't have any other model as well. We have several model instead of Gaussian to be model as our random signal, or to represent our random signal, or to represent our noise. Okay, one of the example that is not Gaussian is what we call as Rayleigh noise. okay, or Rayleigh distribution function. So this is the expression, this is the PDF of Rayleigh noise. Okay, so from here for this slide, I would like to highlight is that the one that I would like to highlight is that you can see here, if okay, let's say okay, this is the shape of this is the shape of Rayleigh noise, the PDF of the Rayleigh noise. Okay, you can see now it's not bell shape anymore, the shape is like this. So remember, the step is similar. You get the image from the plane surface, you generate the histogram, from the histogram you generate the PDF, and if you find out the shape of your PDF is look like this, okay, then you can conclude that the noise that affected your image is Rayleigh noise. And again, if you can see, if you choose and if you conclude that the noise affected your image is Rayleigh noise, then there's a different parameter that you need to measure. Okay, some of it is this one, which is A and B. Okay, from here, then once you find A and B, then you need to measure the mean and variance. Okay, so the step is similar, but now it's more variable or more parameter. If you talk about the Rayleigh noise, you need to find A and B based on the PDF, and then once you find the A and B, then you from A and B actually you need to use the A and B to measure your mean and your variance. So you can see that now it's different. Okay, so mean and variance, if you want to calculate, previously we are using this formula. Yeah, this formula, but this one only applicable for Gaussian noise or Gaussian distribution function. But if you find out your PDF is not bell shape anymore and the shape is look like this, then it's not Gaussian anymore, it's a Rayleigh noise, then the parameter is different. Okay, that's why for Rayleigh noise, there's a 4 parameter that you need to measure or you need to calculate, which is A, B, and then from A and B you can obtain your mean and variance. Now the mean and variance have their own formula for Rayleigh noise. Okay, so that is the step. Okay, so I hope that you can understand. Again, if you talk about the Rayleigh noise, then for example, once you plot your histogram, once you plot your PDF, and then you find out the histogram seem to be something like this. Sorry. So if you find out that your PDF, okay, once you plot, it's look like this. Okay, I just give you some idea there. Okay, now it's not bell shape anymore, it seems to be like the Rayleigh noise. Then what you do, of course you know this one, this point because this one comes from the normalized histogram or the PDF that you measure. Okay, for the one that we have discussed previously in this one. Okay, because this one is Gaussian, the peak is 18/36. Okay, that is the case that we discussed earlier. Just assume that, let's say after you do the PDF, actually this is actually 18/36, the peak one, but now it's not bell shape anymore, it seems to be Rayleigh noise. So what you need to do, then you just take this expression, then it should be equal our 18/36, then you can find our B is what, and then from B, by using this formula, you can get your A, and then from once you get A and B, then you can use that A and B to obtain our mean and variance, which is this one, which is expressed by this one. Okay, sorry, this one is the mean and variance for Rayleigh. Okay, not this one. Okay, this one is a next model. I just point wrong slide there in my previous discussion there. Okay, when you talk about the Rayleigh noise, then if you want to measure the mean and variance, then it depend on A and B. This is the formula, and then of course to get A and B, then you need to obtain to get this peak point, and to obtain this peak point, of course, it comes from your PDF. Okay, once you get all, then you get all the mean and variance, then you can replace this point. Okay, you can then from this expression of Rayleigh noise, then you can replace the A here, and then you can replace the B that you measure here. Okay, any point A and B, you must replace what with the value that you have calculated before. So that's how you do for any noise that you want to estimate, or any noise that you want to investigate. Okay, the all things depend on the shape of the PDF. Okay, if the PDF is in bell shape, then it should be Gaussian noise. If the shape is look like this, then it's a Rayleigh noise. Then you need to measure all the parameter, or I'm sorry, you need to calculate all the parameters involved with Rayleigh noise to fill up all this expression. Okay, the mean, the variance, A and B. So later you can read about the explanation here. Okay, Rayleigh noise is always happen. It's very helpful in characteristic the noise phenomena in the range camera. Okay, range camera is the camera that not provide the color image. It provide the intensity value of that image is represent the distance between that camera and the object in front of that camera. So it's a little bit different camera. Okay, the camera is measure the distance, meaning that the near the how far and how near the object in front of that camera, that distance will represent the intensity value inside the image. Okay, and in general, Rayleigh noise is always happen at this kind of hardware. And then next model is gamma noise or elang noise. Okay, the process is similar. Okay, what you need to do then, if you obtain the PDF, and if the PDF is in this shape, then you need to find out the peak value. Again, the peak value must in the PDF, not the histogram. So that's why if you see in my whiteboard there, okay, if you see in my whiteboard here, okay, I don't proceed this peak, but I proceed this peak, because this is the PDF. So if you want to model the noise, then you need to refer to the PDF, not the histogram. Okay, so same noise. That's why they use here P bracket Z. Okay, that's a PDF. So if you need to find the peak value, then you know what is your K. Once you know the K, then you can use this formula as well as this formula to find out what is A and B, before you can find the mean and variance by using that A and B, and anything, all the variables that you calculate, you must fill in this expression, because this will represent the noise model affected your image. Okay, you can read the explanation there, what this noise is happen in which type of hardware. Okay, another noise model is called exponential noise. So this is the expression, and this is how to measure the mean and variance. Of course, you need, in this case, you only need variable called A. And then if you plot your PDF and you find out this, the PDF is look like this, then you need to find the A there before you can proceed with this expression, or to calculate all the noise, the PDF model for your noise. Okay, so you may proceed to another model, which is noise and uniform noise. Okay, the process is similar. What is uniform noise? So this is how it's look like. If your histogram is like a square, or no, not square, the shape is look like a rectangle, then you just take whatever value that you obtain from the PDF, you must equal with 1 over B minus A. Then you know your A and B here, then you can identify what is A and B. From there you can measure the mean and the variance, then you can express this back by using all the parameter that you have calculated. Okay, the B, the A, and so on. Okay, I believe that you also familiar with this one. Okay, this is SAS and Paper Noise that we have discussed earlier in the previous chapter. actually that is also can be considered as one of the noise model. Okay, if you find you do the same thing, take the plane surface, generate the histogram, and obtain the PDF. If the PDF is look like this, then you can conclude that the noise affected your image is SAS and paper noise. So this is, then you need to fill in all this, because for SAS and for SAS and paper noise, there's no mean and variance. You only have A and B. Okay, this is just some comparison. What are different between all this type of noise model that we discussed before. Okay, if you have some image like this, if you plot the histogram, if this image is free from any noise, then you will find out that you only have 3 bar there, because you have 3 color. Okay, means that this image is free from any noise, or we can say this is actually the ideal image where it's free from noise. So if the image is free from noise, then you should see only 3 bar, because in this case, why we see 3 bar, because we only have 3 colors there. So that's why it should be 3 bar to represent these 3 color. Okay, the difference is just the frequency. Okay, the frequency is depend how many pixel represent by that color. Okay, so if this image is affected with that the noise model that we have discussed before, that is okay, this is how it's look like. Okay, for Gaussian, then you see a bell shape. So we see a 3 bell shape because we have 3 bar there. That's why we see 3 bell shape. And this one is Rayleigh, 3 Rayleigh. And then we see a Gaussian noise, 3 Gaussian. And this is a exponential. This one is a uniform, and this is SAS and paper noise. So that is the difference between that model. So you can see that by using the PDF, you can investigate what type of noise, or in other words, what type of PDF can model our noise that affected our image. So that is what we do right now.